for coming to the talk. Thank you for inviting me. So I'm Xiaolong, I'm from UCSD. So I will talk about manipulations mainly, and then use both simulation and real data. So now if you talk about training and manipulation policy nowadays, a lot of things are actually focusing on real robot data training, right? Using teleoperations, basically human controlling a robot to do things. And on the other hand, there's also recent efforts basically collecting a lot of human videos. Basically, humans are looking alike humanoid, so we can do co-training with human data and human video and robot data. And the problem of all this real world data is that first, if you do teleoperation, it's really kind of painful because wearing VR glass or exoskeleton, you are either very tired on your head or you're very tired on your body. So it's having a very limited scale. And on the other hand, if you want to collect real human data and then co-training with human data, it works well with grasping kind of tasks. But once you have very complex contexts and very complex interactions beyond grasping, so the human hand context and the robot hand contact with the objects are not really the same. So the co-training becomes harder. So instead of real world data, this talk actually want to explore a little bit on the sim data. So essentially, if you want to do simulation training in sim to real, there is going to be gaps in pixels and physics. For the gaps of pixels, we will introduce a work on real to sim, basically scanning objects into simulations and then make realistic, photorealistic sim. And then for the gaps of physics, so there's no really a good way now to build the simulators that has very, very good physics that you can just directly transfer. That is still very, very hard. So instead of building a simulation with very, very good physics, so we basically look into more on how do you leverage both simulation and real data together. So maybe less real data and more simulation, but then the combination of them. So these are basically two topics that I'm going to cover today. To start from this real to sim work, we actually want to go by how the whole pipeline works, right? So from basically designing the task, collecting data, and also evaluations. So this is essentially what every robotics paper do, right? So designing method, collect the data, deploy, and then evaluation. So if you actually do evaluations in the real world, it's incredibly painful. Actually, in a lot of experiments, every time you compute the success rate of robot doing good or not good, it's a human to basically computing the success rate. It's a very tedious job, and then it's actually a job that is challenging your integrity a lot because the student can get very tired, and then it's like, okay, this is kind of right, so we success. So it's very hard to ensure the correct actually, it is actually correct. So of course, evaluations in real data is photorealistic, accurate, but it's very expensive in general. And then in simulations, right? So we have a lot of great simulations. Many skills just we just mentioned about it. And then the problem of simulation is the benefit is that essentially it's low cost, and then you can evaluate as much as possible. But then it's still not as realistic as the real world, and then the physics is also very far away. So what we are proposing this work is the Gaussian splatting world. Essentially, we didn't solve the physics problem, but then essentially we try to build more photorealistic simulation using Gaussian splatting. So essentially, if you can build this kind of simulation world that has photorealistic simulation, and then it's still very low cost, you can keep evaluating it, then you can essentially put it inside the whole design loop, right? So then you can actually design your methods, giving your evaluations feedback. If the evaluation feedback is very fast, then you can iterate the design much faster. It's like if you have label or image-led test set, you can just keep design your method to fit to the test set, right? So this is more like that, but so you can actually have a simulation that help you design the method and then works in the real world. So what we did is basically we actually scan the robot, right? Scan the robot, scan the environment, and on the other hand, we have realistic object data sets to come together. So our method specifically is like we have robot scans. So we have DTC, like the meta data set, and then the YCP data sets, all with very beautiful scans and matches. And then we have this, combine them together, we call this like GSDF. Students call it GSDF because they want to match URDF. So we call it GSDF. It's not really doing anything, but actually just like putting all the scans in the same word coordinate. That's essentially what you do, right? So you have all the collision mesh, and you have all these these scans. Basically, then you can still run your simulation back end. So the simulator we are using is also Sapien for this project. And then the front end is basically using 3D Gaussian rendering to render all these scenes and objects together. So if you can replace the rendering with 3D Gaussian splatting, still using the same Sapiens backend, so then you can do a lot of things like benchmarking and also like designing the method in the loop, keep improving your methods, keep collecting data in the simulations to get better results. So just a brief evaluations on like how realistic these things is, right? So on the left side, you basically are training different methods on different data and different tasks. And then the x-axis represents how good the model works in the real world when you deploy to the real robot. And y-axis represents how good the model works in simulation. So we basically show that this if the performance are pretty much aligned in sim and real if you look at the left side. Of course, simulation is better because you are essentially trained in simulations and then deploy in the real world. So simulation is always have better results, but then it's pretty much the trend is quite aligned that if you get better in simulation, you get better in the real world. On the right side, we also visualize basically if we do teleoperation in the real world and train a policy in the real world, right? And then what is the performance look like? And then when the policy is transferred back to the real, what the performance looks like. So on the right side is always the real world performance is better because it's trained on the real world. But then the trend, again, is the same, that if you perform better in real, then you also perform better in sim. So essentially showing that there is a certain alignment between sim and real. And then because it is aligned, you can essentially also design your methods in sim and then try to transfer real that will work better. And here is some visualization of tasks and how sim and real looks like. On the right is actually simulation. So essentially it's all visualizing the Gaussian splatting rendering. And it takes a few times to grasp it. Maybe it's still not success. And on this, another task is stacking the cans. The task is still relatively simple, but I just want to give you a feeling that essentially the simulation actually looks quite realistic in here. It's almost look like a real robot. It's not that far away. So once we have these simulations and reals quite aligned using this Gaussian splatting, we can actually using Dagger to basically improve the policy, right? So you can do your planning in simulation, train a policy, and then you run in the simulation and then find out some policies fail, and then select the failed trajectories, and then you replan those failed trajectories, and then you use it again as the training data, and then include it in the to basically improve the policy again. So it's like bootstrapping the policies in sim, collect data and training, collect data and training. So the orange line is basically, is essentially in general showing dagger results, and then like blue line shows that it's without dagger, so you can get better and better results with daggers with the simulation in the loop. Showing again some examples are basically, so using dagger and training from scratch. Basically, I remember that the picking the other can was not so successful, and then if you train with dagger in sim, and then you keep improving it, and then you transfer the real, and then the results got improved. Similarly, this is another stacking example, right? Yeah, so a lot of examples are basically the same. So these are works that basically focus on the pixels and then real to sim. It works well because the physics are quite simple, right? So it's just a parallel jaw gripper, so it's pretty large as well and soft. And then grasping, if you get the right pose, it's usually correct. But if we go beyond 2 fingers, if we do multi-finger hands, so we do find out that maybe training on pixels alone are not enough. So essentially in this work specifically, we are trying to also train a simulation policy by using point cloud inputs. We find that the use of point cloud as input for policy A, the explicit geometry is actually quite important when you have like these multiple contexts for grasping. B, it's actually also easier to do sim to real transfer because I kind of get around RGB in this particular work. It just cares about the geometry, right? So, so what we do is, there are a lot of similar work. I don't think we do that different. It's just there's some data curations and some tricks, but in general, it is a generative model using conditional VAE, and then inputs point clouds and also the state parameters of the hands, go to the legworks, and then use the CVAE to generate different poses of how to grasp objects. In the paper, we mentioned how we increase the diversity of the different graphs, how we ensure the grasses to be more successful. So these are the main contribution of the work. I'm not going to go over it, but essentially this is like the general framework, and a lot of other similar work follows this framework. But let's push it a little bit further, right? So can we do dexterity with beyond just grasping? And the work in here is going to be manipulation that is more dynamic and then with even more complex context. Specifically, we are trying to kind of spin pens. It's not a regular pen because the hand is very large, so you can have a larger pen. So the title is called Lessons from Learning to Spin Pens. It's called lessons because it's still not working. So if it works, then we will have the title called Learning to Spin Pens. If it doesn't really quite work, we call Lessons from Learning to Spin Pens, but it's an accepted paper. So essentially what we try to do in here, this is the initial idea. We have some work on using tactile sensing and then rotating pens and things. So we visualize some tactiles. So these tactile sensors are more 0-1 rotations of this like long thing on the hands. So basically, what the framework we are trying initially is also just sim to real, right? Training on simulation and transfer the real. Then it turns out to be incredibly challenging for this particular task. I will show some failure case so that gives you a sense on how hard things are. So you can see we actually have a string hanging these things in here initially when we do experiments. It's just maintaining the balance itself is very hard. And then a lot of other distribution cases sometimes just not do anything. And then we also find out that there's a trade-off of how heavy the object you can put on the hands, right? So if the object is too heavy, then it's very easy to fall. If it is too light, then it will not activate the tactile sensor. The tactile sensor also needs like certain level of force applied to activate it. So that is very tricky. So we eventually actually just give up the tactile sensors. We just remove it. We spend a lot of time to design the fingertip, but then we throw them all away. And then what we find out is that this is actually before, maybe 2 weeks before the deadline. Nothing works. And then the student basically think that can we actually try to deploy these things in open loop. Open loop meaning you just don't care your observation of the object at all. You just keep doing these motions, like pretending nothing is interacting or nothing happened, right? So you put a pen on this, and then you train a policy in C, and then you just deploy it open loop. And then it sort of works a little bit, right? So you actually can rotate the objects a little bit. So then basically, the student basically say, oh, can we actually now, since we have some success example, then can we actually start collect data in the real world using these sort of success examples? So that's essentially what we do. So our simulation policy is not really directly deployed as a closed loop policy now. It's actually used as kind of open loop replay kind of thing. It's really just generating the trajectories in the real world. But you sort of need this initialization because this task is very, very hard to tally up with, right? So the human hands and these hands are completely different. This only have 4 fingers, human hand have 5 fingers, and the contexts are very different. So without the simulation training, you will never get a runnable trajectory in the real world. So you still have the simulation training. But then if you do closed loop, it's very easy to generate out of distribution case. The pen is falling, and then the fingers go crazy. So then you can only deploy it in the open loop way to generate some useful trajectories. So when you generate these trajectories in the real world by open loop replays, you can try to retrain these policies and then deploy in a closed loop. So this is essentially some results we have eventually. This is deploying in closed loop. Basically, you are collecting some data in the real world, and then deploy it, and train and deploy it. We still have some numbers on this fingertip because it was originally designed to put on some tactile sensors. We just remove all of this. And then basically, this is another example showing that you are doing the things. So this observation is only taking the proprioception of the state of the hands as input, like every joint positions and velocity as the input. It doesn't take any visual and any tactile sensing. This is also similar to what Haozhi was doing in his first work on this in-hand rotation things. Basically, the positions of the and joint positions and velocity of these different motors essentially indicates where the object is. Right, so more examples are actually generalized to different objects. But again, I think we call this as like lessons because this does not really work that well, right? So we have like maybe 10-ish objects pick out that actually works. And so that's it. It doesn't really work on many objects, right? And here are some failure cases we see quite often. So basically, it's falling is mostly the problems that your control frequency is not fast enough. You slowly, and then when the object falls, you don't get fast react enough to actually to put it up. And then as you're rotating the objects can drift. The center of mass basically drift away. So then there's nothing that can prevent it falling as well. So this happens a lot. It's still a very fragile system. But in general, I'm happy because it actually starts working for this like long stick in-hand rotation. It has never been working in multiple objects before. Usually you need to tune an optimal controller to work on a single object. So it's kind of proven learning can work on this task as well. Now, we say lessons from learning to spin pens, right? So what are the lessons? So the first lesson is really the deadline is the source of creation. So then the reasons that we have conference and deadlines are actually quite important that this will not happen if it is not because of like there's only 2 weeks before the deadline, and then we have to do something. So this really happened because of the Coral deadline. And sim training still requires extensive designs. For this particular task, I didn't go into too much detail, but essentially, it's very important, for example, how you initialize the position of the pens. You need to kind of initialize the pen's positions in like you designed many different orientations. It's not randomly initialized, right? So the reward of how to rotate these things are also quite important. So this task has some crazy reward designs, basically. And for this kind of very dynamic context, sim-to-real does not directly work. It's much more difficult than grasping. A lot of in-hand rotation tasks, you can see it as like, specifically for this task, you can see it as a test bed of how do you push extremes on like creating the largest sim-to-real gap in physics. So this will be the task. But even if it does not work, simulation is still quite useful for exploring the skills, right? So like I mentioned, you cannot really tally up this task. It's just very different methodology. So simulation is quite useful to explore the initial skills that can start rotating things. And then you can bootstrap in the real world, collect more data, and then to make it actually work. So I like this because it's really a very good use of combination of sim and real data, right? It's not only just relying on sim and do sim to real. It's not only just doing like real world data collection, teleoperation. It's kind of combinations of simulation plays a part of getting the initial trajectory, and then real world plays part of bootstrapping from these trajectories. So that's the part I really like about this work. Right, so to do a quick summary of takeaways, so I introduced basically almost 3 works. So to handle some pixels for sim to real, we can use real to sim. And then point clouds are quite useful as observations when you are using hands and then do sim to real. And then eventually we need to find smarter way to basically leverage both simulation and the real world, especially for very rich and dynamic contexts when you are doing complex manipulation tasks. And that will be all. Thank you, and let me let any questions work.